Hi Rockers, this is Mrs. Berger, and today we'll be discussing how to solve absolute value equations and inequalities. So this will be the algebraic portion. We'll get a little bit of graphing today, and then we'll wrap up graphing in the next class. So real quick, I would like to walk you through the little Algebra 1 review warm-up so that we can get you started on remembering these things, these concepts of inequalities. This does relate to absolute value, I promise. So on this first question, let's think about how to solve this inequality. It's very, very similar to how we used to solve equations, in that we do PEMDAS in reverse to isolate that x, right? So instead of going this way, we go in reverse. So we take care of adding and subtracting first. Anything that we need to add or subtract on the outside of this variable, we'll tackle that first. There's nothing to be done there. Somebody already subtracted a 30 to put it over here. Then we tackle multiplying and dividing next. If we see this out here, this is the next thing we'll tackle, so we divide both sides by -3. And remember, anytime you have an inequality and you divide by a negative to isolate the variable, you're going to want to switch the direction of your inequality. So that'll leave you with a 6x plus 2 on the left, and then we switch the direction of the inequality, and then we have a -10 on the right. Then we finish out with, there are of course no exponents to tackle, so then we finish out what's going on inside these parentheses here. In order to continue to isolate x, we subtract 2 from both sides. Subtracting 2 from both sides does nothing to the direction of the inequality. We get to keep it as a less than. And then we divide by 6 to get x is less than -2. And then when somebody says to graph this on a number line, what we mean by that is you've just said that any number less than -2 will make this a true statement. By solving down here to get x by itself, you're saying if you put in anything less than -2 in for x, you'll make a true statement. The stuff on the left will be greater than 30. And so to depict that on a number line, you can indicate the -2 here, and remember, since it's less than but not equal to, we indicate an open circle at the -2. And we're saying everything less than -2 is a candidate here for x. So we're saying if you choose any number in the whole wide world of numbers less than -2 for x, you will make a true statement up here. Okay? I'll let you do number 2 on your own or with your teacher. Number 3, the only slight difference is we've got this OR here. Hopefully you saw that in Algebra 1. It just means you need to solve this and solve this, and you'll have 2 parts to your answer for P, okay? So for instance, on the left, we would subtract 3 from both sides, divide by 2, and that's one part of our answer. Another part of our answer, we would subtract 9 here, divide by -1, and again, flip the direction of our inequality. And so this whole thing is the solution to this. If P is less than 2 or greater than or equal to 7, you'll have a true statement up here. Okay? That's how that works. And then this is an and we'll see much more of these today. Hopefully you recall looking at these. These are these little 3-parters. We've got something is less than this expression, and it's also less than this expression. In order to isolate the values of k that make this whole thing a true statement, we start by trying to dig k out of this mess, right? And so the first thing we would do, there's nothing to add or subtract. We would need to divide everything by 5 simultaneously. So we'd have -3 is less than 3k minus 2, and that's less than 4. Add 2 to all sections. You'll have -1 is less than 3k is less than 6. Finally, let's isolate k by dividing by 3. So we have k is less than 2 and greater than -1/3. That's the and, okay, that little sandwich there, that's the and. And if you were to depict these, check this out. An OR statement looks like this. Solid circle, go in this direction, open circle, going this direction. Whenever you have an OR, They shoot off into two different directions. If you have an and, it makes a sandwich. So if you have negative 1/3 here and 2 here, for this particular one we've got open circles for both, and k is sandwiched between those two. So it is less than 2 and greater than negative 1/3. So that's what an and looks like. So hopefully that's bringing back some memories. So let's take those concepts a little further into our conversation today about absolute values. So if you look at absolute value, you're actually talking about a piecewise function, a function that has two different parts to it. Whenever you have a value that is greater than or equal to 0, it acts like a climbing line. Whenever you have a value that is less than 0, it acts like a falling line. Okay? So our absolute values always look like a V for graphical purposes. And look, it's acting one way in this piece and another way in this piece. So when your teacher says this is actually a piecewise function, that's what we mean. Okay? Now, again, we'll get into graphing a little bit more next class, but let's talk about algebra here. When we say absolute value of x equals 3, we're actually asking the question, what numbers, what values of x have a distance from 0 that is 3? So if you were on that number line and you were at 3, if you're at 0, what numbers are 3 away from 0? Well, obviously, 1, 2, 3. 3 is 3 away from 0. But check it out, we have another value. 1, 2, 3. Negative 3 is also 3 steps away from 0. And so that's why there are always two parts to our answers to these. The steps we use to solve absolute values are here. The very, very first step we do is we isolate the absolute value portion. Get these bars or whatever's inside of them by themselves. There should be no junk glued to the front, and there should be no stuff added or subtracted outside. By the time you're ready to take step 2, everything should be isolated. Okay? Step 2 is we need to set up two parts, and we'll show you that probably on the next page. And then step 3 is to solve each part, just like we did in the warm-up. So let's take a look at number 1. Number 1 says the absolute value of x equals 8. Step 1 says isolate the absolute value portion. That's been done for us. There's nothing glued to the front, or there's nothing over on this left side except the absolute value portion. So step 1 was done for us. Step 2 says set up two equations. 1 equals the number, so we take the stuff inside the bars and make it equal to the number. And we take the stuff inside the bars and make it equal to the opposite sign number, or the evil twin, negative 8. I call negative 8 the evil twin of 8. Okay? And these are the two answers. We don't really have any solving to do. X is already by itself, and we've already gotten the job done. But again, if we go back up to our little colored notes up here, what numbers have a distance from 0 of 8? Well, 8 and negative 8 do. Let's kick it up a notch here. Number 2, isolate the absolute value portion. Already done for us. There's nothing glued to the front, and there's no adding or subtracting going on. So this is done. Step 1 is done. Step 2, set up two equations. One set is equal to the number. Take everything inside the bars, 2x minus 3, and set it equal to the number. That's the first part. And take everything inside the bars, 2x minus 3, and set it equal to the evil twin. Now we solve, because unlike the first one, we don't have x by itself. We have a couple more steps to do. So we'll add 3 to both sides, divide by 2. There's the first part of our answer. Add 3 to both sides, divide by 2. That's the second part of our answer. We have two answers to this. Absolute values should always have two parts to their answers. If that went too fast for you, go ahead and pause and replay that. Alright, number 3. A couple more steps here. Step 1 is always isolate the absolute value. That has not been done for us here. Check this out. This negative 10, this subtract 10, is muddying the waters here. So in order to get these bars by themselves, we have to add 10 to both sides. And when we do that, we have 22 over here. Now the bars are isolated, and we can break these into two parts. X plus 1 equals 22. And x plus 1 equals its evil twin, negative 22. Obviously, we have one last step to isolate x. We would subtract 1 from both sides in both parts. x equals 21, x equals negative 23. And you can just say and for both of those. Please note, when you are taking these steps to isolate the absolute value, do not forget to redraw your bars. Those are your notation that you have not yet broken this stuff out of absolute value jail. This step right here, this two-phase setup, is the only time when you get to get rid of the bars, the absolute value bars. They need to stay with you until it's isolated and you're breaking it into two parts. Okay? Now, if someone ever asked you to graph this solution on a number line, you would simply graph negative 23 with a single point and 21 with a single point. Since these aren't inequalities, they're just point solutions, you would just graph them on the number line as points. Okay? Let's take a look at number 4. So number 4 has a step of isolation that needs to be done first. So that step is to divide by negative 2. Again, we have absolute value bars still here. And when we divide by negative 2, we have 4 over here. Now the absolute value is isolated. We can move to step 2. Step 2 is to break it out of jail. So let's break that out. 3x minus 1 breaks out and is set equal to its number. 3x minus 1 breaks out of the jail and it's equal to its evil twin. Now we solve for x just like we've done over and over and over again. Solve for x over here. And these two answers, 5/3 and negative 1, are your solutions. Always two parts for absolute value. Remember, it's a piecewise function. There are two pieces. All right, let's take a look at number 4. And again, we can graph that on a number line. It's just 2 points plotted at negative 1 and 5/3. Now, take a look at number 5. We have some isolation to do. We've got some junk glued to the front here. We've got this 1/2 glued to the front. We need to get rid of that. Do you remember what property we get to use to counteract this 1/2? We need to multiply by the reciprocal, right? We need to multiply by 2 over 1 on both sides. That's what's going to turn this into a 1 and get rid of it, okay? So by multiplying both sides by 2, we're left with the absolute value of 3x minus 1 equals negative 16. Now we have an isolated absolute value. We can break this stuff out of jail. 3x minus 1 equals negative 16. Oh, hold on. We've got a situation. When you have the absolute value of something equal to a negative, when this absolute value is isolated, and you see that it's set equal to a negative number, is that possible? Can you ever have the absolute value of something, which always spits out a positive number, equal to a negative 16? No, that will never happen. You'll never have something breaking out of an absolute value bar. This is always going to spit out a positive number or 0. It's never going to equal negative 16. So instead of setting up our two stages here, we needed to have paused and said, wait a second, it's not possible to be equal to a negative if I'm absolute value. So there is no solution to this. That didn't happen here. Absolute value equals 4, totally possible. X plus 1 equals 22, totally possible. Absolute value of something equal to negative 16, not going to happen. So there's no solution to this. That's a special case. Another special case we have is all real numbers. Okay, and we'll take a look at those in the inequalities. Alright, speaking of inequalities, let's take a look at what we have here. So these ask what numbers, what values of x have a distance from 0 that is less than or equal to 3. Less than or equal to 3. So basically we're saying if I'm 0, what values are between 3 away here and 3 away here? So everything in here would solve this inequality. These aren't just point solutions, they're ranges of numbers. Okay? And once again, we have a 3-step process for solving these. Number 1 is always isolate the absolute value portion if it's not already done for you. Second step has a little decision, a little set of the decisions we need to make. We need to set up an AND conversation for a less than symbol. We need to set up an OR for a greater than symbol. Some people remember this as less than for the AND. and greater for the or, if that helps. And then we would solve each inequality. So let's dive into the examples to show you what we're talking about. So first and foremost, is this isolated? Is there anything around these bars that we need to get rid of first? Nope, it's all isolated, we're all set to go. The next question is, once this is isolated, are we talking about a less than and or a greater than or? We're talking about a less than and. So our setup for setting up these two parts of the equation, when we break this out of absolute value jail, is x plus 5 is less than 4, the regular old 4, and x plus 5 is greater than negative 4. Solve each side. X is less than negative 1, and x is greater than negative 9. Proper notation for this is like this. These are sandwiches. Remember, ands are sandwiches. So x is less than negative 1 and greater than negative 9. And a number line would look like this. Negative 9 here, negative 1 here, open circle, open circle. Everything in between is a solution. So this is our algebraic, and this is our graphical depiction. That's a less than and. Let's take the exact same numbers and do a greater than. Okay? Once again, step 1's done for us. There's no isolation work to be done. Step 2 is taking a look at whether this is less than or greater than, and this time it's greater than, so that's greater or. So when we break these out of absolute value jail, we set up an x plus 5 is greater than 4, or x plus 5 is less than negative 4. Notice when you set up the evil twin, you flip two things. You flip the direction of the inequality, and you make the evil twin number. Flip the direction of the inequality and make the evil twin number. The only difference is the word that's in between. So let's continue to solve, very similar to the other one. X is greater than negative 1, or x is less than negative 9. Sorry about that, negative 9. This is your algebraic response to this. Numbers that qualify greater than negative 1 or less than negative 9 solve this, make this a true statement. Let's take a look at what this looks like on the number line. If we're at negative 9 and values less than negative 9 suit us, that's what that looks like. If we're at negative 1 and values greater than negative 1 suit us, that's what that looks like. So remember in our warm-up, less thans look like sandwiches, the ands look like sandwiches, the ors shoot off in two different directions. That will always be the case. So if you have a greater or, they should go in two different directions on the number line. If that doesn't happen, something must have happened in the solving, so go back and check your work. They should not be going in the same direction. They should either sandwich, go towards each other, or go away from each other. Alright, let's take a look at number 8. Now, number 8 has a little bit of isolation work that we need to do. We need to divide both sides by 3 to isolate the absolute value. And remember, those absolute value bars come along for the ride during these isolation steps. If I divide both sides by 3, I am now greater than or equal to 2. And now that this absolute value is by itself, we can set up our two parts. Let's break it out. X minus 2 is greater than or equal to 2, greater, or x minus 2 is less than or equal to negative 2. I flipped the direction of this and the sign of this. And I said or because this is greater. A couple steps to isolate the x's. Add 2 to both sides. And our algebraic response to this is x is either greater than or equal to 4 or less than or equal to 0. It's an or. This stuff should shoot off in two different directions. 0, 4. I'm greater than or equal to, so I'm solid circles at these values. And if I'm less than 0, I go this way. If I'm greater than 4, I go this way. Shooting off into two different directions, it's an or. That's what I was expecting. If at any point you need to pause and go back through this because I'm going too fast, please do so. Alright, let's take a look at something very similar, except instead of greater than or equal to, we have less than or equal to. Once again, we cannot make any decisions until we isolate this absolute value. So let's do that now. Divide by 3. Now, break this out of jail. Now that it's by itself, now that the bars are by themselves, let's break this out. X minus 2 is broken out of jail. It's less than or equal to 2, which is what we started with. Less than and x minus 2 is greater than or equal to negative 2, the evil twin. We flip this and we make this negative. Continue to solve. Add 2 to both sides. Add 2 to both sides. We have an and in between. Proper notation for this is that nice little sandwiched expression. I'm greater than or equal to 0 and less than or equal to 4. And we'll portray that sandwich on the number line. 0, 4, solid circle, solid circle. Everything in between will make this statement true. Anything between 0 and 4, including 0 and 4, when put in here, will make a true statement appear. And you can certainly check your work as well. Pick a number in between, or pick 0, or pick 4. Put that in here, and you'll see that you've made a true statement. Okay? Alright, let's take a look at 10. Any isolation work we need to do here? Absolutely. There's nothing glued to the front, but there's definitely this pesky little -1 here, so let's take care of that. Leave the absolute value bars. We haven't broken this guy out yet. Add 1 to both sides. Now break this stuff out. 2x plus 4, you're out of jail. You're less than 10. Less than and 2x plus 4, you're greater than -10. Okay? So we do the solving steps for these guys. Subtract 4 from both sides. Divide by 2. Subtract 4 from both sides. Divide by 2. This is an and. Proper notation would be the -7 is less than the x, and the x is less than the 3. That's the proper notation on that. And of course it looks like a sandwich. -7 and 3. And again, we were expecting a sandwich because it's an and. Alright, let's take a look at this number 11. We have a couple of steps. Now let's do PEMDAS in reverse to isolate this. Okay, PEMDAS in reverse. So the last part of PEMDAS is adding and subtracting. So let's take care of this first. Please do not divide by 2 first. That's a common mistake. We need to do PEMDAS in reverse. And the last things in PEMDAS is adding and subtracting. So let's subtract 1 from both sides and carry everything else down while we're doing that. Okay, so if we subtract 1 from both sides, we have 24 on the right. Now let's divide by the 2. Again, these absolute values are coming along for the ride the whole time until isolation. Now that we're isolated, we do two-stage setup. 3x minus 9 comes out of the bars, and it's greater than 12. Greater or 3x minus 9 comes out of the bars, and it's less than -12. Add 9 to both sides. Divide by 3. Oh, I apologize. That should be greater than. Add 9 to both sides. Divide by 3. And this is an or. There's nothing else to be done with notation, so you can just put a big box around this. And then the drawing, the number line, -1 is down. Oops, that's a -1. -1 is down here. 7 is here. Open circles for both. I'm either less than -1 or I'm greater than 7. It's shooting off in two directions, which is what we expect for an or. Okay? Now, your homework includes a few special case examples. Some of them are no solutions, some of them are all real numbers. So make sure you take some time on those. Make sure you understand why those answers are all real numbers or no solution. Think about the properties of absolute value. Absolute value things will always spit out positives, not negatives. Okay, so I'll leave you to that. Obviously, come with questions on that homework if that didn't make sense. Now, let's introduce you to a little bit of graphing some absolute value investigations. Let's take a look at this problem and sort of get us ready for next class. We've got a diver going through ocean search and rescue training. So they're diving off maybe a diving board or a boat up here. And this measures how deep they are in the water, and this is how much time it takes for them to make that progress. What information can you determine about the dive from the coordinates of the point 5, -8? So if we go 5 over 5, -8, right here, what is this telling us? What is this point telling us? Think about that for a minute. What are we interpreting? If you need to pause the video, pause and think for a minute. What does this mean? What does this represent? This bottom of this V shape, this bottom of this absolute value graph. Well, you should say that is talking about the fact that the diver has reached the lowest point, which is 8 feet below. 8 feet below water, or 8 feet deep below the surface, 5 seconds after they started diving. Okay, so that's how we should interpret this. This graphical representation of reality is telling us that it took 5 seconds to reach its bottom depth of 8 feet deep. If that's the case, what is the average rate of descent for the diver in the water? So once they get in the water, what's the rate of descent in the water? How do we determine that? Anytime we think of rate, the word rate, hopefully you remember from Algebra 1 that rates are often found on graphs when we look at slopes. So maybe we look at the slope of one of these lines. If we take a look at, let's say we go from, let's see, this is an easy to find point here. 1, 0 is 1 point. And 5, -8 is a point we've already talked about. If we have those 2 points, and you can pick other points as well, these are just ones that I chose to use. If we have these 2 points of, oh, my apologies down here, 5, -8, and 1, 0, can we find the slope or the rate of descent of this? Can we find the slope of this part of the dive? Absolutely. We have formulas for this, right? We have the slope m equals y2 minus y1 over x2 minus x1. Hopefully this is ringing some bells from Algebra 1. So for us that means 0 minus a -8 divided by 1 minus a 5. That's 8 divided by -4. That's -2. That basically is saying my rate of descent, negative being descent going down, my rate of descent is 2 feet per second. That diver is going 2 feet per second. Okay? So then let's talk about which point on the graph shows the starting location of the diver. Let's go back and look at this. What's the starting location of the diver? Do they start out in the water, or do they start out above the water? They start out, time of 0 starts here. So this right here, 2 feet above the water, is the point that describes its her starting point. So 0, 2, 0 time, 2 height, 0, 2 is the point at which she starts her dive. 0 seconds. What does the V shape of the graph tell you about the dive? Hopefully you're starting to think V shapes for absolute values. We'll talk about that again next class. What do the points where the graph crossed the x-axis tell you about the dive? Well, first of all, what does the V shape tell you? It basically says the diver went down and then they went back up again, right? That should be fairly straightforward. So the diver dove down and then swam back up. That's what the V shape tells us. And what do the points where the graph crossed the x-axis tell us about? If they cross the x-axis, if the x-axis is the surface of the water, and below the axis is below water, and above the axis is above the water, the x-intercepts here, where the graph crosses the x-intercepts, what do they mean in reality? That means where the diver entered the water and where the diver exited the water. Okay, so that's how you interpret that in real life. This graph is all great in mathy words, but when we get into real life, what does this mean? What does what does 1, 0 and 9, 0, what do those coordinates mean? Well, this one is where she entered the water, and this is where she came back out of the water. Okay? Alright, let's take a look at our Desmos activity, and I might not go through the entire thing. I might just do a little bit, but on your phone or your device, you should be Googling absolute value transformation Desmos. And we're going to take a look at this great tool. We're going to be in Desmos a lot this year. Take a look at this great tool. So when you Google that, this should be your first hit. Now if we click on that, it takes us right to this wonderful tool talking about absolute value graphs. Okay? And you'll notice that the overarching graph that's depicted here is of the form y equals a times the absolute value of x minus c plus d. And we're going to investigate what happens when we mess around with the values of a, c, and d. That's what this exercise is taking us through. So right now we've got this great absolute value graph that looks like a perfect V. It's got an up 1 over 1 type slope going on the right, and an up 1 back 1 on the left, and we're in basically a standard form here. Now the directions ask you to first slide the variable d to a positive number and take a look at what that does to the graph. And we can do that. If we slide the variable d, this guy right here, slide the variable d to a positive number, let's take a look at what that means. As we go positive, what does the graph do? It moves it up. It moves it up above the x-axis. When d was 0, make it back. When d was 0, it was right at the x-axis, right there. And when we make it positive, it goes above it. And of course, the next question is, if we move it to be a negative number, it drags it below the x-axis. Okay, so that's what we want you to see there. Now the directions then ask you to put d back to 0. And now we're going to play with c. We're going to slide the variable c to the number 2. So let's slide c and see what happens. If we make c into 2, what happened? We moved the graph, we picked up the graph and we moved it right 2. So whenever a value here increases, we move right 2. Whenever a value here increases, we move up, however many steps we put. What if we slide the variable c back to negative 2? That's right, it goes left 2 spaces. So a positive c, in this format, if a c is positive, it goes right. If a c is negative, it goes left. Now notice the format here is negative. We'll dig into this next class. It's a little bit tricky. This one here, if d is a positive number, it goes up. If d is a negative number, it goes down. Okay? So let's set those guys back to where they were. You were a 0, and you were a 0. And now we're going to play with a. A we kind of treat like a slope. Okay? It makes it skinnier or wider. So let's take this. Its default is a 1. In our standard form, it's a 1. The parent function a is just is an invisible 1. So that's why it's sitting at 1 right now. If we make it more positive, greater than 1, take a look what happens. It gets skinnier, okay, or more steep. The slope is more steep. If we turn to a negative number, or less than 1, if we go less than 1, it gets fatter. It gets fatter and fatter and fatter as we turn into these decimals. See these decimals, these positive decimals make it fatter. And then if we cross over, if a turns into a negative number, we go upside down completely. You see that? Upside down completely? I highly encourage you to play with this, right? And as you're doing it, think about what numbers you're changing in our parent equation up here. And just play around with it. Questions 7, 8, 9, and 10 allow you to play with it in a directed form, but definitely make use of this application to really get a sense of what happens when you change these values, so that when you do them by hand or on your calculator, you can see why. Okay? I hope this was helpful. Please pause and replay anything you need to, and let us know if you have questions on homework.